The game confronts two opposing armies in battle. The winner will be the side that can defeat all of the opposing units first. In each turn, all of the units can be moved up to a certain number of tiles and attack a single opposing unit.
The red units are controlled automatically by the CPU. In order to do that, we implemented the Dijkstra pathfinding algorithm to find the shortest route from each of the red units to the closest blue unit. The CPU moves and attacks with each of the red units before giving control back to the player.
A previously defined number of game objects are instantiated in an array, but are not drawn. Afterwards, an emitter object generates trajectories for these objects that depend on certain parameters, such as how many particles per second and how much lifetime each particle will have. This emitter then calculates the position in which every particle should be, and then makes the respective draw calls.
The layout of the map and the initial positions of the red and blue units are defined in textures. Each pixel of these textures represent a tile in the game. In case of the terrain, the color of the pixels represent the type of the terrain in the scene: grass, forest, or rocks.
We added an effect that makes things far away clouded by fog. We accomplished this via the fragment shader by combining the output color with gray, proportional to the distance from the camera to the object that's been rendered. The fog is activated only when the camera is below a certain height and can be toggled by a uniform variable. A previous idea we had was to use the depth values of the rendered pixel to calculate how much fog the pixel had. This idea made the fog grow in a plane in front of the camera. That didn't look very realistic.
We added an outline to some of the objects in our scene. That way they get highlighted and it's easier to spot them. The color and width also changed to differentiate between a player and enemy units, also to highlight the currently selected unit. To identify the pixels that are part of an outline, we store the unique ID of the object that is drawn in each pixel on an additional FBO. In a deferred pass, we check the pixels around the current fragment. If there are any with different object IDs, we paint that pixel as a border. The first approach we had for this was to detect borders with the angle of the normal relative to the camera. This made very rough models to have borders everywhere, and even smooth models have terrible looking borders.
The player has an ability to turn back time and redo their actions. When this power is activated, the colors of the scene are turned to their negative counterpart in a growing circle, and the circle shrinks when the power is deactivated. To apply the effect to only the pixels in the circle, we draw a sphere on the stencil buffer. On the second pass, we sample that buffer. If it's not blank, the corresponding pixel has their colors inverted. We ran into a problem while implementing this. To make the effect, we sampled the stencil buffer in the fragment shader. The stencil and depth data are combined into the same buffer. That restricts us to sample both of these datasets simultaneously. The toon outline originally sampled the depth buffer. That's why we needed to store the depth data in the outline FBO in order to use it for that effect.
We changed the way in which the objects in the scene are lit to make a crisper border between shadow and light. The steps we took are the following. In the fragment shader, we calculate how much the current fragment is being lit by the light sources in the scene. We get a number from 0 to 1. We call it the light power. We sample a texture using this light power as the x-coordinate. This texture is a grayscale gradient. We use the value sampled from this grayscale to obscure the output color of the current fragment to create the toon-like illumination. The gradient texture can be designed to create the light to shadow transition as script or smooth as we want. We also made it so the objects don't obscure completely when no light is hitting them, so we had a clearer scene overall. A mini-map of the terrain is shown at the left bottom corner of the screen. That map is a low resolution off screen render from a camera that is always sitting on top of the stage.
There are a lot of identical objects in our scene: terrain blocks, trees, and rocks. To make a more efficient use of our resources, we store the position, rotation, and scale of these objects, and make a call that draws the same mesh multiple times, applying the transformation that we previously stored. That way we can render very big maps, as large as 4900 tiles, at a playable frame rate.
How would we improve it? We could add different type of units, like an archer who has a longer range, or a cavalry unit with more movement, or maybe add multiple scenarios, like when the player beats the AI once, the game continues to the next harder map.
If we continue this game idea, even though it works with our current engine, our opinion is that it was a tool to learn, and if we want to continue on the path of making a product, we would probably remake it in an existing engine, to add more gameplay and features in an efficient way.